Welcome to today class of nonlinear vibration. So, today class we are going to discuss about different ordering techniques in the nonlinear equations what you have derived before using different methods. So, here we will discuss about the scaling parameters, bookkeeping parameters, and also we will discuss about different nonlinear equations used in this course. So, before going for this ordering technique, so let us see what are the systems we have already discussed. So, for examples we have discussed about the simple pendulum. So, in case of simple pendulum already you have seen how we have written the equation motion in a nonlinear form. The linear equation motion already you have already you know. So, it can be written in this form, that is theta double dot plus g by L sin theta equal to 0. So, here for small value of theta, so sin theta equal to theta, and this equation reduces to that of a harmonically excited system, that is theta double dot plus g by L sin theta equal to 0. So, the motion is simple harmonic. So, but if theta is not small, in that case one has to expand this term sin theta up to its third order or fifth order or higher order and write the governing equation motion. Similarly, one can see this simple spring mass damper system. So, in this case the spring may be a linear spring or it may be nonlinear spring. So, depending on the hardening or softening type of springs, so one can write different equation of motion. So, in this case the equation of motion one may write in the simplest form, that is in the form of Duffing equation, which can be written in this form, that is m x double dot plus k x plus alpha x q. So, if I will write the cubic nonlinear term, so for free vibration I can write this is equal to 0, or for force vibration I can write this equation in this form, that is f cos or sin omega t. So, here f is the forcing parameter or amplitude of forcing, omega is the frequency, and m is the mass of the system, k is the stiffness of the system, and alpha is the coefficient of the nonlinear term. So, we can add the damping also to the system. So, by adding damping this left hand side I can add C x dot term. So, in this way we can write the equation motion. So, for this simple spring mass damper system. Similarly, when we have number of springs added or number of dampers are added to the system, so we can write the equivalent stiffness and equivalent damping of the system, and taking the nonlinearities effects into account we can write the equation of motion. So, one can observe. So, in case of this spring mass system, so when it is executing the simple harmonic motion, that means when the spring we have considered to be linear. So, in this case if we have the spring force let F is the spring force versus this displacement. So, if it is linear, so then we have the equation motion in this form, that is m x double dot plus k x equal to 0, and in this case the system will exhibit simple harmonic motion as one can observe from this plot. So, in this plot, so it shows a sinusoidal curve. So, when we have the linear spring, then we can have a simple harmonic motion, but if the spring is not linear, then we can have a nonlinear type of response, which we have to determine how the response of the system is obtained with time, or how the system responds or how the system behaves with time. The dynamics of the system can be obtained from either one can plot this dynamics of the system by doing this experiment, or analytically one can determine the response of the system. So, similarly, we have studied other different types of systems also. So, here this is a bridge system which can be modeled as a beam with many spring and damper system in between. So, one can have different layers of the beam. So, here one has put 3 layers of beam, beam 1, beam 2, beam 3, or the soil can be modeled, sometimes the soil or breeze can be modeled in this way. So, in that case also one can find the response of the system. So, the response may or may not be simple harmonic. So, if one consider the spring and damper to be nonlinear, then one can obtain different type of response. So, what type of response one will get, that thing we will study in next module, but in this module we are interested to know about the equation of motion. So, already we have seen we can use different type of equation, different type of methods, for example, Newton's second law, D'Alembert principle or Lagrange principle and Hamilton principle to derive the equation motion. So, after deriving this equation motion, so we can find the coefficient of these equations to see the or to perform the ordering of the equation. So, before that let us see some of other type of systems. So, in previous systems what we have seen, so here we can use fixed coordinate systems to find the equation motion, but sometimes it may require to define the moving coordinate system. For example, in this case of this Puma robot, Puma is programmable universal, PUMA, programmable universal manipulator machine for assembly, programmable universal machine for assembly. So, this Puma robot one can use. So, here another type of robot, that is a humanoid robot also. You can see the image of the humanoid robot, or in this case of Puma robot. So, we can fix different coordinate system. So, these coordinate systems can be fixed at the joints. So, in this case this is the fix, one can fix the fixed coordinate system here. So, also one can fix the coordinate system here also in this joint. So, we have 6 different joints. So, 6 joints are there in this Puma robot. So, here we have 3 joints. So, yaw, pitch and roll motion in the wrist, and in addition to that we have 3 degrees of freedom here. So, this rotates about this base, also it rotates about this base, and it has a revolute joint here also. So, we have 3 major motion about these 3 axes, and we have yaw, pitch and roll motion above the wrist axis. So, we have 6 degrees of motion, and it can take any object from the. So, it can take. So, using this end effector, it can take any object from its workspace. So, while deriving the equation motion for this type of system, so here one has to use this Euler-Lagrange type of equation or Euler-Newton type of Euler-Newton formulation to derive the equation motion. So, we have not studied this equation Euler-Lagrange or Euler-Newton formulation. The interested reader can read those things from the books, robotics related books. So, in this case, so we have one moving coordinate system and fixed coordinate system. This is the fixed coordinate system. In addition to, we have this moving coordinate system. So, to find what is the torque required at this joint, that means we are putting a motor at this joint, we have to put a motor at this joint. Also, at the joints we are putting different motors. So, at the joints we required to find what is the torque required at those joints to manipulate this robot. So, to find this torque, so we have to write the dynamic equation motion. So, by finding this dynamic equation motion, so one can obtain the response of the system. So, similarly, in case of this humanoid robot, to move this joint, so for example, these fingers, to manipulate these fingers. So, in that case one has to know, so what is the torque or force has to be applied by the tendon. So, there are several tendons in this humanoid robot. So, in this humanoid robot also one can put the motor also at the joints. So, one has to find what is the force or torque required at the joints in this robot. So, in that case one has to write the equation motion. For example, one can write the equation motion by using this equation, that is tau equal to m q double dot plus g q q dot plus g or f q equal to 0 f q. So, here this is the inertia force. So, this will contain the potential function like k x spring, and for example, it is equivalent to this stiffness of the system. So, this contain the gyroscopic force due to gyroscopic couple or Coriolis component, and by taking these dynamics into account one can find the torque required. Sometimes it is not possible to model this equation correctly. So, for that purpose one has to use this control parameter, or one can use this control K p, let it is proportional gain. So, K p into E. So, if there is some error plus then K d into E dot. So, where E is the q desired minus q actual. So, error is q desired and q actual, and q is the joint variable. So, m is the mass matrix. So, taking all this into account, so one can write the dynamic equation, and after getting the dynamic equation, so one can check whether the system vibrates or not by solving this equation motion. So, in this way one can, or another example is also there, this is a satellite system. So, in the satellite system these are the solar panels, and also we have different mechanisms to actuate these things. So, one has to write the equation motion for the system to study the dynamic of the system. So, to find the equation motion for different systems, already we know we can use this Newton's second law. For Newton's second law, then D'Alembert principle, then so Lagrange principle, and Hamilton's principle, extended Hamilton principle. So, already we have discussed about these methods, and we know that this Newton's second law or D'Alembert principle we can use for systems with few degrees of freedom, for example, single or 2 degrees of freedom system, and this Lagrange principle can be conveniently used for multi degrees of freedom, and this Hamilton principle one can use conveniently for continuous system. So, continuous system. So, here this is multi degree of freedom system, and these two for single or 2 degrees of freedom system. So, in case of Newton's second law, so we are drawing the free body diagram of the system. After drawing the free body diagram of the system, we separate the whole assembly by drawing the free body diagram, and then we write the force equilibrium equation. For example, we write the external force will be equal to mass into acceleration if this external force F is acting on the system and it is accelerated with acceleration A. So, we are writing the equation motion in this form, and in D'Alembert principle. So, we can write this external force plus this internal, this is the inertia force equal to 0. So, this is D'Alembert principle. where this Fi, that is the inertia force equal to mass into acceleration, and it takes place in a direction opposite to that of acceleration. So, we can put a negative sign. So, by using this D'Alembert principle or Newton's second law, we can derive the equation motion for single or 2 degree of freedom system conveniently. Similarly, in case of Lagrange principle, so we can write the equation motion in this form, that is d by dt of del L by del q k dot minus del L by del q k, plus if damping is present in the system, we can write del d by del q k dot equal to q k. So, where this q k, that is the generalized force, is written as summation I equal to 1 to n. So, F I dot del R I by del q k. So, here this let n number of forces are acting on the system, then writing the position vector as R I. So, one can do this dot product to find this generalized force q k, where q small q k is the generalized displacement or generalized vector. So, this is the generalized coordinate, q k is generalized coordinate. For example, we have already discussed that in case of the simple pendulum. So, our generalized coordinate is theta, theta is the generalized coordinate. Instead of putting this x and y, x I, y I or x 1, y 1, one can put this theta at the generalized coordinate. So, here x and y are the physical coordinate. So, here L, capital L is the Lagrangian of the system, that is equal to kinetic energy minus potential energy of the system. Similarly, one can derive the equation motion by using Hamilton principle. So, in case of Hamilton principle, so the equation can be derived by using this formula, integration T 1 to T 2 delta L plus delta W n c dt equal to 0. So, where this q k vanishes at T 1 or q k T 1 T 2 equal to 0. So, q 1 vanishes at T 1 and T 2. So, L is the Lagrangian of the system, delta W n c is the non-conservative work done by the system. So, by using this extended Hamilton principle also we can derive the equation motion, but in case of continuous system, unlike discrete system, we have the equation motion is a function of both space and time. So, in case of continuous system, it is a function, this displacement parameter is a function of both space and time. So, in that case, to reduce it to its temporal form, already we have discussed that we can use this we can use the Galerkin's method, generalized Galerkin method. So, we can use the Galerkin's method to reduce the equation from its space and time to its temporal form. So, in this way we can derive the equation motion. This is just a review of what we have studied in this module. So, in this way we know how to derive the equation motion of the system. For example, in this case of simple harmonic, in this case of simple pendulum, the equation motion can be written in this form theta double dot plus g by L sin theta equal to 0. Now, expanding the sin theta, we can write theta double dot plus g by L theta minus g by L theta q by 6 plus g by L theta q by 120 equal to 0. So, now we are going to study how we can order this equation, so that our analysis will be easier, or we can do the analysis in a simplified way. So, here one can, by taking this g equal to, let us take this g equal to 10 meter per second square and L equal to 1 meter. So, taking this example g equal to 10 meter per second square and L equal to 1 meter. So, this equation can be written in this form, that is theta double dot plus 10 theta minus 1.6667 theta q plus theta 0.0083 theta to the power 5 equal to 0. So, looking at this example, looking at this coefficient. So, coefficient of theta equal to 10, coefficient of theta q equal to 1.6667. So, which is almost 10 times less than that of the linear coefficient, that is coefficient of theta, and this term, that is the coefficient of theta to the power 5, which is 0.0083. So, it is almost 1000 times less than this linear term. So, one can conveniently neglect this term, that is theta to the power 5, and one can write this equation in this form, that is theta double dot plus tan theta minus 1.6667 theta q equal to 0. But still one can neglect this term also, this coefficient of, as the coefficient of theta q is very small, that is almost 10 times or 7-8 times less than that of linear term. So, in that case one can write the linear equation, that is equal to theta double dot plus tan theta equal to 0. So, that equation already we have discussed, that in the linear case, that is theta double dot plus tan theta equal to 0. But if we are not neglecting this term, that is we are not assuming that theta to be small, then we have to take into account these terms. So, in that case we can keep up to order of this coefficient of theta q, that is we may have to keep the equation in this form or write the equation in the form, that is theta double dot minus 10 plus tan theta minus 1.6667 theta q equal to 0. But still if we require more precision, we have to keep all the term, that is we may keep up to this quintic order. So, this equation, what equation we have written before, that is theta double dot plus tan theta minus 1.6667 theta q plus 0.0083 theta to the power 5 equal to 0. So, in this way we have to keep up to quintic order. So, in analysis of nonlinear system, it is very important to check the coefficient of the terms, coefficient of this. So, here the coefficient of theta is 10, theta q equal to 1.6667 and theta fifth equal to this. So, we have to write this coefficient in such a way that we should not fail to neglect these terms. So, to write this equation in a modified form, so we can use some scaling factor or bookkeeping parameter. So, let us assume that, or let us take this theta equal to p y. So, by taking this theta equal to p y, okay, so let us taking theta equal to p y. So, we can substitute it in this equation. So, now the equation become p y double dot plus tan p y minus 1.6667 p q y q plus 0.0083 p to the power 5 y to the power 5 equal to 0. Now, by suitably choosing the parameter p, so we can manipulate these coefficients. So, now this equation is written. So, now first dividing this p throughout this equation. So, we can write this equation in this form, that is y to the power y double dot, that is d square y by dt square plus tan y. So, this is the linear part. So, you just see in the linear part we do not have this p term, but in the nonlinear part we have the p term remaining. So, in this cubic order we have this p square term, that is minus 1.6667 p square, and in this quintic term we have this 0.0083 p to the power 4. Now, by suitably choosing this p parameter, so we can order this equation or we can write this coefficient in such way that so this coefficient will be of the same order as that of the linear part. That means, So, we have to choose p in such way that this 1.6667 p square may be nearly equal to 10. So, let us take some value of different value of p and check how the equations look like. So, for example, taking p equal to 10. So, if you take p equal to 10, so this equation now becomes y double dot plus 10 y minus 166.67 y cube plus 83 y to the power 5 equal to 0. So, in this case one may note that these two coefficients are very large in comparison to linear part. So, that means this will behave as a strongly nonlinear system. So, if you take this p equal to 10. So, now taking p equal to 5. So, we can write the same equation in this form, that is y double dot plus 10 y minus 41,667 y cube and 5.1875 to the power 5 equal to 0. So, in this case one may note that while this quintic coefficient of the quintic order, that is 5.1875 is almost near to or of the same order as that of the linear term, that is 10. So, but this cubic term is 4 times. So, this is 41 and this is 10. So, it is 4 times higher than that of the linear part. So, if we are interested to keep this coefficient to that of the linear order, so we can now play with this number p and we can choose this parameter in such way that they will be of the same order. For example, taking this p equal to 2, now we have the coefficient of the cubic order less than that of the linear part, that is 10. So, this becomes 6.6668 and the quintic part becomes 0.1328. So, now almost it is this quintic part is 100 times less than that of the linear part, but this cubic term is of the same order as that of the linear part. And by putting p equal to 3, so we can get this cubic order to be 15.003, which is slightly higher than this linear part, but this quintic part equal to 0.6723. So, by choosing p equal to 2.5, so we got almost the cubic order term to be same as that of the linear part. This is 10.412969. So, this equation becomes y double dot plus 10 y minus 10.4169 y cube plus 0.3242 y to the power 5. So, this way by taking different value of p, so we can write the same equation in different form. So, where one can have a system similar to that of a hardening spring, or one can have a system with that of a softening spring, or one can write these, or one can have this coefficient very high or low order. So, this hardening or softening spring term will come. Let us take this p equal to minus. So, if you take p equal to minus 10, so instead of this minus sign we can get this plus sign. So, in case of minus we are getting the softening type of spring, but if we have this plus sign we can get this hardening type of spring. So, if we take p equal to minus 10, so in that case p square will be equal to 100. So, it will not be negative, but we can have this fifth order term. So, fifth order, so this becomes fourth order. So, in this case, in this particular example, as we have this p square and p fourth. So, by taking different value of p, whether positive or negative, we can get only this equation or the coefficient negative. That is why, so always we can have the, so we will not get a positive term or positive coefficient, and so the spring type will be that of, if we compare this thing with that of a Duffing equation, this will show the response as that of a softening type of spring. And okay. So, now we have different type of equation. We have seen how by taking different value of p, we can control the coefficient and we can get different equations. So, let us use another form. So, the same equation theta double dot plus tan theta minus 1.6667 theta q plus 0.0083 theta fifth can be written in this form also. So, by dividing and multiplying this term by epsilon, where epsilon is a bookkeeping parameter which is very less than 1. So, we can write the equation in this form, that is we can write this equation theta double dot plus tan theta minus epsilon. So, we have multiplied epsilon and divided epsilon here. So, now by dividing epsilon in this equation, so what we can write? So, we can get this term equal to 16.667, which is almost of the same order as that of 10. And here also in this case, by dividing this term by epsilon cube, you just see we have multiplied this term by epsilon cube and divided this term by epsilon cube. So, our coefficient, so here the coefficient becomes 8.3 and here the coefficient becomes 16.667. So, one can write this same equation in this form, that is theta double dot plus tan theta minus epsilon into the 16.667 theta q plus epsilon q into 8.3 theta to the power 5 equal to 0. So, here this term 8.3 and 16.667 cannot be neglected with respect to the term 10. But when we are writing the equation in this previous form, that means theta double dot plus tan theta minus 1.6667 theta q plus 0.0083 theta to the power 5 equal to 0. So, there is a tendency always to neglect the cubic and fifth order term, but when we are using this bookkeeping parameter epsilon, so as the coefficient are of the same order as that of the linear part, we will, so there will be no tendency to neglect these nonlinear terms. So, now let us take another parameter, that is epsilon equal to 0.1667. So, in that case we have this equation or the coefficient becomes 9.9982. So, which is almost near equal to 10 and this coefficient becomes 1.7917. So, in this way by using this epsilon parameter, so this epsilon is known as a bookkeeping parameter. So, by using this bookkeeping parameter, which is a small number that is less than, so this epsilon always less than very less than 1. So, by using this bookkeeping parameter, so we can order the equation motion. So, here we know now by using the scaling parameter or by using this bookkeeping parameter, we can order the equation of the motion, So, the same equation what we have written here. So, we have used the coefficient of theta to the power 5 as that of the order of epsilon cube. Also one can write, so when I have written it is of the order of epsilon cube. So, then the coefficient becomes 1.79, but this is not the same order as that of the linear part, that is 10. So, I have to increase this value, or so I have to write this is of the order of epsilon to the power 4. So, the same equation can be written in this form, that is theta double dot plus tan theta minus epsilon into 9.9982 theta cube plus epsilon to the power 4 10.7482 theta to the power 5 equal to 0. So, we can write our equation. So, that is, let me write a general equation in this form, that is theta double dot plus omega n square theta plus epsilon alpha theta cube plus epsilon cube beta theta to the power 5 equal to 0. So, if we will use the forcing in this system, so we can write this equation in this form also, omega n square theta plus epsilon alpha theta cube plus epsilon cube beta theta to the power 5 equal to. So, I can take this forcing to be of the order of epsilon. So, then I can write this equal to epsilon f cos omega t. So, here this omega, that is the external frequency, and this omega n square, or from this omega n. So, this is the natural frequency of the linear system. So, natural frequency of the linear system. So, most of the time in case of our nonlinear system, we may be interested to study the external frequency to be nearly equal to that of the natural frequency, or we may be interested to study the summation of the natural frequency, sum of different natural frequency. For example, in continuous system, we will have a number of natural frequency of the system. So, in that case, one may be interested to study different frequency. So, in first case, so that is when omega nearly equal to omega n, to study the nearness of this external frequency to that of the natural frequency, one can use a parameter. So, that is known as detuning parameter. So, one can write this omega equal to omega n plus epsilon sigma. So, here sigma is known as the detuning parameter. So, one can use detuning parameter to write the nearness of the natural frequency to that of the external frequency. Similarly, in this case, that is when omega nearly equal to omega n plus omega m. So, one can have a combination type of resonance condition. So, in this case omega nearly equal to omega n, one can have primary resonance condition, and in this case one can have this combination resonance condition. So, in case of combination resonance condition also one can study this omega nearly equal to. So, one can study omega nearly equal to, let me take only the first two modes. So, it will be omega 1 plus omega 2 plus epsilon sigma. So, this will, so in this case, so we have taken only the first two mode. So, this external frequency nearly equal to summation of the first two mode frequency, and we are studying near the, so we are studying near the summation of these first two mode. So, here epsilon is the bookkeeping parameter and the sigma is the detuning parameter. For example, so let omega 1 equal to, so let us take omega 1 equal to 20 radian per second and this omega 2 equal to 60 radian per second. So, in that case our omega, so we can study this omega near 20 plus 60, that is 80 plus epsilon sigma. So, to study the nearness of this, so generally one can take this near to 10% of this thing. So, we can, so if we are taking 10% of 80, so that means we can vary this thing from 72 to 88. So, we have to study the frequency near to 72 to 88 radian per second. So, in that case we have this epsilon sigma equal to, so when it is 88, so our epsilon sigma equal to 8, by taking this epsilon equal to 0.1. So, we have this sigma equal to 8 by 0.1. So, this is equal to 80. So, we can have a value of sigma nearly equal to 80 to have this omega, that is the external frequency near to 88 or near to 72. In case of 72 also, so this epsilon sigma, so we will have a negative sign here. So, this epsilon sigma equal to 8 and sigma will be equal to 80 also. So, we can vary this detuning parameter to study the resonance different resonance condition. So, previously I told about the primary resonance condition, that is omega equal to omega 1 plus epsilon sigma. So, when this natural frequency nearly equal to the external frequency. So, in case of a forced vibration of the system, so we can have the primary resonance. So, this is primarily observed in case of the linear system, but in case of nonlinear system, in addition to this primary resonance, so one may have secondary resonance. For example, one can have the subharmonic oscillation or the superharmonic oscillation corresponding to. So, for example, this omega 1. So, if omega 1 nearly equal to 10 radian per second. So, we can have the secondary oscillation or secondary resonance condition. Also, we may have, so omega 1. So, this capital omega nearly equal to twice the omega 1, that is nearly equal to 40 radian per second. So, we may have subharmonic resonance, and when it is equal to 10 radian per second, we may have the other type of resonance condition. That means, when it is away from the natural frequency, that is away from this 60, also we can have resonance condition. So, in case of nonlinear system, so we can have this superharmonic and subharmonic resonance condition. So, now let us see some commonly used nonlinear equations and some system which behave or which give rise to those type of equations. So, our familiar equation motion what we have studied till now is the Duffing equation. So, the commonly used different type of nonlinear equations are this Duffing equation, Van der Pol equation, Hill's equation and Matthew equation, and a combination of all these equations. So, for example, in spring mass damper system we have this. So, in case of the spring mass damper system, the equation is that of the Duffing equation type. So, in this Duffing equation type we can have this quadratic nonlinearity or we can have cubic nonlinearity. So, this is cubic nonlinearity. One can add quadratic nonlinearity or quintic type of nonlinearity, what already we have seen gamma x to the power 5. So, by adding different type of nonlinearity to the system, so we can write this Duffing equation. The simplest type of Duffing equation is x double dot plus omega n square x plus 2 zeta omega n x dot plus alpha x cube equal to 0. So, that is for the free vibration case, and in case of force vibration we can have the forcing term in the right hand side. So, epsilon f cos omega t in the equation. So, a number of variation of this equation can be written. So, this Duffing equation for free vibration by putting equal to 0, Duffing equation for force vibration can be written in this. For force vibration also we can have two variation. So, in this case we can have the strong nonlinearity or weak nonlinearity. So, in case of weak nonlinearity we can remove this term epsilon and we can write the equation. So, that is f cos omega t, and in case of strong nonlinearity we have f cos omega t, where this f is of the same order as that of the omega n square, and in case of weak nonlinearity we have epsilon f. That means, this epsilon f will be at least one order less than that of omega n square. Similarly, we can have multi frequency excitation. So, here we have a single frequency excitation. So, we can write the equation in this form, that is x double dot plus omega n square x plus 2 epsilon zeta omega n x dot plus epsilon alpha x cube. Here we have taken one order less in cubic nonlinearity. So, it may be written equal to f 1 cos omega 1 t plus f 2 cos omega 2 t plus, so we can put 2 or 3 terms f 3 cos omega 3 t. So, in this case, for example, in case of a linear system, already we know if this equation is in this form, that is x double dot plus omega n square x equal to f 1 cos omega 1 t plus f 2 cos omega 2 t. We can use superposition theory to write the solution of the system, but when we have this nonlinear term in this equation, we cannot use the superposition theory and one has to find the response for each case. That means, one has to find the response of the system first for f 1 cos omega 1 t. So, one has to find the equation motion by considering all the effects. So, in this case, one may note that the resonance condition may occur when omega 1 nearly equal to omega n square, similarly omega 2 nearly equal to omega n square or omega 3 nearly equal to omega n square. Also, it may occur when the combination of these omega 1 plus omega 2 will be nearly equal to that of omega n square. So, one can have combination type of resonance also in this multi frequency excitation. So, one can have simultaneous resonance condition. Simultaneous resonance condition means this omega 1, omega 2 and omega 3, capital omega 1, omega 2, omega 3 simultaneously will be, as they are independent, they simultaneously equal to that of the natural frequency, and so in that case one can have the simultaneous resonance condition. Similarly, one can have this, one can have this equation is written for a single degree of freedom system. So, one can write the same equation that for a multi degree of freedom system by writing this x as in the vector form. So, that means x double dot plus omega n square. So, in this case this omega, or I can write this equation in this form, that is m x double dot plus k x plus. So, I can have some other matrix, that is, so which will contain this damping C is a function of x dot, and we can have this F, another matrix or damping matrix will be a function of x dot. We can have this forcing term is a function of x dot t, and another forcing term which may be a function of x and x dot. Similarly, we can have this external force F external. So, it is a function of time. So, this may contain this x dot, and we can have some term also which is function of g. So, it is a function of x and its higher order, like, so it may contain the nonlinear term like x cube x square nonlinear term. So, x square x cube some nonlinear term. So, this will be a function of some nonlinear term. So, in this way one can write the equation motion for multi degree of freedom system. So, writing the equation of multi degree of freedom system, then one can reduce this equation by using modal reduction method. There are several modal reduction method available, and then one can use this ordering technique to order these equation. So, after ordering these equation, one can then go for the solution technology, which will discuss in the next module. So, instead of using this Duffing equation, there are some more types of equations which we have also considered. This is Van der Pol type of equation, x double dot plus x equal to mu into 1 minus x square into x dot, one can use a combination of this Duffing equation and Van der Pol equation. Similarly, one can have this Hill's equation in this form, that is x double dot plus p t x equal to 0, and Matthew equation in this form, that is x double dot plus delta plus 2 epsilon cos 2 t x equal to 0. But by adding these Matthew equation or Hill's equation or Van der Pol equation with Duffing equation and taking different type of forcing parameter and ordering these equations, one can have different sets of equation of motion which will correspond to different type of nonlinear systems what one can study in this course. So, in this way one can order the governing differential equation motion by either using the scaling parameter or by using this bookkeeping parameter. Sometimes both scaling parameter and bookkeeping parameter has to be used to order the system. So, let us take some exercise problems to. So, let us take some exercise problem. So, use scaling parameter. So, one can use scaling parameter to write this equation. So, the equation 3 x double dot plus 30 x minus 0.1 x square plus 0.05 x cube equal to 0, x double dot plus 20 x minus 1.5 x square plus 2.7 x to the power cube equal to 0. So, x double dot plus 50 x minus 0.5 x square plus 0.3 x cube equal to 0.1 sin 2 t. So, these two are for free vibration, this is for force vibration. So, one can write one more equation, that is for multi frequency. So, x double dot plus, so this is 50 x minus 2.5 x square plus 1.5 x cube equal to. So, let us put some strongly nonlinear system, that is 5 or 45 sin 2 t plus, let me put another forcing term which is of 5 sin 4 t. So, in this case this forcing term, that is 45 sin 2 t. So, the coefficient is of the same order as that of the linear part, that is why this is of the same order as that of the linear part, but this forcing, the coefficient of this forcing term is 10 times less than that of the linear part. That is why one can use a bookkeeping parameter epsilon in this case. So, in this case use the scaling parameter and bookkeeping parameter to order. Keeping parameter to order these equations to make the nonlinear terms as same as that of the linear part. So, in this way we have studied, in today class we have studied the scaling parameter and bookkeeping parameter, and we have seen different type of nonlinear equations such as Duffing equation, Van der Pol equation, Matthew equation, then Hill's equation, and a combination of all these equations, and one can know different type of forcings also, single frequency, multi frequency, different resonance conditions, that is primary resonance condition, secondary resonance condition, subharmonic resonance, superharmonic resonance condition, and in addition to that we have this combination type of resonance. Also we have simultaneous resonance conditions observed in this case of nonlinear systems. So, in the next module we are going to study about how to solve these equations, these nonlinear equations by using both qualitative and quantitative methods. So, in quantitative methods we will study different perturbation techniques and harmonic balance method to find the solution of the equations. So, in the fourth module we are going to or in the fifth module we are going to study different nonlinear techniques to find the solution of these nonlinear equations. Thank you.